In part A of the problem, we solve for the bubble point pressure at a temperature of 30 degrees Celsius. For part B, we now want to calculate the dew point pressure at a temperature of 30 degrees Celsius. Okay? And so just like we saw in ICP 3, to calculate the dew point, you have to solve the following equations. Okay? And so we're going to have x1 plus x2. That's going to be equal to 1. And we plug in our modified Raoult's law rearrangement. We could replace y2 with y minus y1. Okay? Alright, and then here we're going to have pressures in both terms, so we could factor out and isolate it. So now P is going to be equal to this. Right, and because we're dealing with the vapor phase mole fractions here, the pressure we're going to get is going to correspond to the dew point pressure. Okay? All right, and so to calculate the dew point, we're dealing with an equal molar mixture. So we would plug in y1 is equal to 0.5 here. And then once we get the dew point pressure, we could calculate the liquid mole fraction of that liquid droplet, that first liquid droplet that forms. And it's going to be equal to this. So this is just a rearrangement of the modified Raoult's law. Okay? So I'll call this equation 1 and equation 2. So the idea here is we would use these two equations to solve for P dew and x1. Okay? But because we are now accounting for non-idealities, there's now a severe complication in our problem. And that has to do with the activity coefficient. So we see that the activity coefficient shows up here, another one here, and then also in our x1 calculation. Right? And so our activity coefficients, remember, they're following this form, where they're the exponential of A times the mole fraction. And so what this is saying is that in both of our equations, both of them are going to be functions of x1. Right? And so now we have, when we're dealing with just the simple ideal Raoult's law case, we could solve all these things. We had to solve them simultaneously, but at least they were sort of like linear equations. Now we're dealing with equations that now have exponentials of x1s in the denominator, right? And so now we have very nonlinear equations that we need to deal with. And so in this case, rather than solving for x1 and p dew explicitly, we now have to do some sort of nonlinear sort of computation in order to calculate them. And so you could do this calculation using MATLAB. But what I want to show you actually is an approach where you could do this sort of calculation by hand. Okay? And so this sort of ties back to the homework problem where you were looking at a mixture of water and ethanol, and you wanted to calculate the volume of the mixture, and you had to do it by an iterative sort of method. Okay? And so what we're going to do is we're going to do a calculation that is in that same vein. So to solve for P dew and x1, we're actually going to do some iteration by hand. Okay? All right, and so I'm going to go through the different steps of how you iterate by hand. Okay? And so when you're iterating by hand, the first thing you need to do is you need to make an initial guess. Okay? So you need to make an initial guess for something. And you have different choices. You could make an initial guess for x1 or p do, but what I'm actually going to suggest is that we make an initial guess for the activity coefficients. Okay? And so what we're going to do is we're going to guess that gamma 1 and gamma 2 are both equal to 1. Okay? All right, we're going to assume that they're both equal to 1. So essentially we're saying we're dealing with a ideal solution. All right? So we'll make those guesses for gamma 1 and gamma 2. And then what we'll do is we're going to go back to equations 1 and equations 2 and plug in those values for our guess, so that we could get some sort of estimate for p do and x1. So let's go through that. So if we start with equation 1, we have p is equal to this. And if gamma 1 and gamma 2 are equal to 1, then all we have in the denominator are the vapor pressures. Okay? So we could plug in, so this is going to be 1 divided by, we have 0.5, 0.249 bar plus 0.5, 0.159 bar. If we do that, now we have 0.192 bar for our estimated pressure. Now that we have a value for pressure, we're going to go to equation 2. Okay? Which was this. And once again, we're sort of assuming that gamma 1 is equal to 1. Okay? And so now that we have an estimate for P, we could plug that in. So 0.5 times 0.192 bar divided by 0.249 bar. Okay? And now, by plugging in for pressure, we now have an estimate for x1. And then, since we're dealing with a binary system, we could also get x2. Alright, so now, by just making an initial guess at gamma 1 and gamma 2 equal to 1, we now have x1 and x2 values. What we're now going to do is we're going to use those x1s and x2s to estimate the activity coefficient values. So now use x1 and x2 to calculate gamma 1 and gamma 2. Okay? So gamma 1 we know is equal to the exponential of a x2 squared, 0.432 times 0.611 squared, and that's going to give us a value of 1.175. And if we do the same thing for gamma 2, we get a value of 1.068. Okay? And so what we see now is that, initially we guessed that gamma 1 and gamma 2 were equal to 1. But now that we've kind of gone through a cycle of calculating all our values, we see that our activity coefficient values have updated. Now, gamma 1 and gamma 2 are both larger than 1. Now that we have these new values for gamma 1 and gamma 2, we then repeat the cycle. So we're going to go back to equation 1, and we're going to recalculate a new pressure. So P is going to be equal to y1, gamma 1, it's not 1 anymore, so it's going to be there in the denominator, 1 minus y1, gamma 2, P2 sat. Alright, and so we now have these updated values for gamma 1 and gamma 2, so we could plug them in. If we do that, we see now our pressure, before we had 0.192 bar, but now our pressure has increased to 0.212 bar. Now that we have this new pressure, we could update our estimate for x1. So now it's 0.367, so that's lower than the x1 value we had on our first iteration. And we also get x2 is equal to 0.633. Okay? Alright, and now that we have these new x1 and x2 values, we can then use them to go back and calculate gamma 1 and gamma 2. And so you keep repeating these iterations until your new guesses are basically the same as the old guesses. And so, just like you probably have seen in computations, you could keep track of all these iterations just by using, a table that looks like this. P bar. Okay? All right. And so, in this table, we start off just saying gamma 1 and gamma 2 were equal to 1. Then we estimated a value of p bar of 0.192. In fact, let me move this to the side and just say iteration 1, 2, 3, 4. Okay? Oops, actually, I misaligned. 1, 2, 3, 4. So here's our first iteration. Okay? Alright, so we start off with an initial guess of 1, 1 here. Update our estimated pressure. And then we estimate mole fractions. We estimate new gamma 1s and gamma 2s. Right? And then we keep updating all these values. 60, 0.212 bar, 0.362, 0.638, 1.192, 1.058, 0.212 bar. And so by the time we get to the fifth row, we see that our x1 and x2 values are basically the same as the previous iterations. Okay? And so, depending on what your tolerance is, at this point, we could say, all right, our answers have converged. And so, from hand iteration, we could estimate that our P due is equal to 0.212 bar, and x1 due is equal to 0.361. Alright, and so here we used a hand iteration approach, which is a sort of old school approach for doing these sort of calculations. Of course, we now have access to software tools that allow us to do these iteration sort of calculations automatically. And so you're welcome to do this calculation, write a MATLAB script to do it. And if you did write a MATLAB script to do it, I wrote one, I'm not going to show the details, but essentially you would find that your answers basically converge to this. Okay? And so even if you use MATLAB, you would find that the numbers you get there would be actually very similar to the ones you do with a hand iteration. Okay? Of course, that depends on the sort of equations that you're using. In this case, with these bubble point or the dew point calculations, hand iteration converges pretty quickly. There could be more complicated equations where it would take many more iterations for your numbers to converge.